In breaking particle physics news, the observation of the highest energy neutrino ever measured has just been announced by the KM3net collaboration. If you're new here, then welcome. My name is Clara, and I am a particle physicist working on the ATLAS experiment at CERN. And here we talk about particle physics, obviously, the building blocks of our universe in the very smallest forms, and also the forces that govern how these particles interact with each other. In particle physics, there are essentially two main ways in order to study the fundamental building blocks of our universe. At CERN, where I work on an experiment on the Large Hadron Collider, we accelerate protons and sometimes heavy ions to almost the speed of light, and then crash them together in the center of giant detectors. This is a really useful way to study new particles in a controlled manner, creating them momentarily in the center of these detectors so that we can study the particles that they change into and learn more about their properties. However, this does mean that we are limited by the energy that we can reach with our machines. The second way to study elementary particles is to make use of the fact that nature has its own particle accelerators, such as black holes and other cosmic phenomena. Particles created in these events end up whizzing throughout our universe until some of them eventually reach us. And then we can build detectors either here on Earth or send them out into space and observe these particles coming towards us. This allows us to not only study the particles themselves, but also to learn more about the cosmic phenomena that cause them to get so quick. Throughout most of human history, we've been limited to only studying photons. These are the particles of light, but at different wavelengths, we're studying radio waves, microwaves, and other energies of the photons. But in the last century, we have been able to expand this to include neutrinos and even gravitational waves, the very shaking of the fabric of our universe. And one of the experiments that studies neutrinos here on Earth is called KM3net. And this experiment is just in its infancy. It's still being built. But today, they had a rather large announcement to make. So I spoke to 3 of my colleagues working here at NICEF in the Netherlands who are in this collaboration to find out why they're building an entire detector just to measure neutrinos and why the results that they've just announced is so exciting.
Hello, I'm Clara. I'm a PhD student at NICEF and I work in the KM3net telescope, which is a neutrino telescope.
I am Aart. I'm a physicist working at NICEF in Amsterdam, and in this experiment my role is that I'm a physics coordinator, so I coordinate all the science programs that we do.
Hello, I'm Paul de Jong. I'm a physicist at the University of Amsterdam and at NICEF. I'm currently the spokesperson for KM3net.
So KM3net is a project that is constructing a neutrino telescope in the Mediterranean Sea. That means we look for these particles, elementary neutrinos, that come from space, and we built a detector to detect these particles.
So neutrinos are a particle that interacts very weakly, which means that it's very difficult for them to interact. So for example, they can traverse the Earth and just escape, and they don't feel any matter, or just like traverse all the universe and keep going. So to be able to see some neutrinos, so to be able to see the interaction of these neutrinos with some matter, we need to have a very large volume. So we use the water itself of the sea as a medium where some neutrinos will pass by and interact. So as larger is the volume we are looking at, the telescope, more probability we have to see a neutrino.
Well, it's sort of originated by the fact that we see charged particles coming from space with enormous energies. So these are called cosmic rays, and they've been detected already 100 years ago. And they can have really enormous energies, like a factor million times larger than what we can do in the LHC, for example. So it's immediately, to particle physicists, immediately interesting, like where are these particles produced? There must be particle accelerators in the cosmos of enormous power, and yeah, we just want to understand basically how these particles get accelerated and what kind of processes happen there. But also it's kind of a free laboratory to study the neutrinos themselves. As you know, as particle physicists, we want to understand the fundamental properties of these particles. So it's also a free source of particles that we can study, and in a complementary way as that we can do with accelerators on Earth.
You know, if you talk about putting a neutrino telescope at the bottom of the Mediterranean Sea, everybody is amazed. And so was I when I first heard about it. So it's a fantastic experience.
Before we dive into the result that was announced, I wanted to understand more about this detector and how you even build something kilometers down at the bottom of the Mediterranean Sea. How does that even work? But before we do, I need to tell you about a physics phenomena called Cherenkov radiation and how it's used in neutrino detectors. Now, you might be aware that nothing can travel faster than light is traveling in a vacuum. But when light is traveling through a substance like water or ice, it's actually traveling slower. And therefore, it's possible for another particle to travel faster than the light is traveling through that substance. When this happens, it gives off a glow of radiation, similar to a sonic boom when an airplane breaks the sound barrier. Neutrino detectors like KM3net use an array of light sensors to detect this glow and not only measure the path of the particle through the substance, but also learn more about its properties.
The detector is located at the bottom of the Mediterranean Sea. It consists of lots of these glass spheres that you see here. So basically what this is a pressure-resistant sphere, and it has lots of sensors for photons, for optical light that we want to detect. So what we do is we equip a large volume of seawater with a lot of these spheres, and then they detect light. So we see lots of light that's not so interesting, but sometimes a relativistic particle goes through the detector, and we see correlations of this light on multiple spheres. And then we get excited because such particles must have originated by a neutrino interaction that happened just before we observed the event. So that's what you see in kind of this picture. So here you have all these spheres. They are located along lines that are roughly 800 meters in size. So this thing is really sort of kilometer scale. And this is a computer program that draws each time when we have detected some light, it draws one of these little cones. And so this is what we do. We search for patterns in these lights, and we are able to reconstruct in the end the trajectory of these particles that go through by seeing, so the particle in this case is a muon, but there must have been a neutrino prior to that. And we can very accurately reconstruct the direction of this particle. So we know that there must have been a neutrino from some particular place in the universe. So we point them back and we see if there's some interesting astronomy going on there. And in the end, we want to learn this way. We want to basically learn more about the highest energy astronomy objects in the universe.
So these are the optical modules of the telescope, which means that those here are the eyes of the telescope. So each of these is a photomultiplier tube, and it detects photons, light. So we have many of those. In this line here, we have 18 of these optical modules that we call, and each optical module has 31 eyes. And with this, we detect the light that the neutrinos, when they come in and interact close to the detector, they create this light, and we detect it with them. So we build them, integrate them, all the pieces together, put the electronics inside, and then at the end, when we have a whole optical module built, we connect them among each other. So we connect these 18 optical modules. And the connection you can see here, it brings the power to each of the optical modules. And also it has an optical fiber which brings the data at the end to the shore.
The Aart detector consists of individual strings, lines with these spheres, domes we call them on them. And we put these lines individually down on the seafloor, and we connect them to the cable there. So we are still building, but at the same time, all the lines that are already there have been turned on and are taking data. So we're continuously taking data, although we're also still constructing. So the particular event that we have seen was found when we had 21 lines of the detector on the seafloor and operational. By now it is 33, for example, for Aart. And it will continue to grow and eventually until about 200, 230 lines for the Aart site.
So during my research, I mainly did two things. One of it is to calibrate the positions of the detector. So because it's under the sea, the detection units and the telescope itself moves with the sea currents, because you have to imagine that this is 2-3 kilometers underwater and there is sea currents. So we have to track every time the movement of the telescope to see where the telescope is pointing at. So that's one thing I've been working on. And the other thing is to search for dark matter with the neutrinos that we see with the telescope. So we try to see if in regions where we know there is dark matter, we see neutrinos coming from there, and then relate the existence of dark matter with neutrinos.
I'm excited, of course, because the detector will still grow and we'll be able to take much more data. There are two physics sides to the detector. One is the high energy cosmic neutrino side, so that's where we have seen this one event. One event is just one event, so I'm looking forward to more high energy events, at least seeing what the data will show. I'm looking forward to finding sources inside our universe where these neutrinos come from, because these are the sources of the highest accelerators that exist in the universe. The other side is a little bit finding out about neutrino properties. So the other part of our detector is actually focused towards somewhat lower energy neutrinos, where we will measure oscillation physics. And I'm really looking forward to a competitive result, and in fact the first neutrino mass ordering determination.
Could we take a look at inside one of the modules that's being tested?
Yeah. Come. So this is the testing room. Now we are doing some tests. So before closing the optical modules, we have to do some tests previous to that, because when we close them, it's very difficult to open them again, because we fill them with a gel that solidifies when it stays still. So first we do some checks to each of the photomultiplier tubes, the eyes of the telescope, and also we do some checks of the electronics. And when this is done and the optical module seems right to be integrated, then we do checks with the already built optical module. So this is a black box. When we close it, it's completely dark. And then, for example, what we do is to check the dark counts. So how many photons or signals the eyes detect when in principle there's nothing. So we need to calibrate many different things.
And this is noise from the electronics?
Exactly. And for example, each of the optical modules have also an acoustic receiver. And the acoustic receiver is used for the positioning of the telescope. So as I said before, the telescope moves like this with the sea currents. So we have an acoustic positioning system. So we have acoustic emitters, and then each of these optical modules receives those acoustic emissions, and then with that we compute the distance and then find the position of the telescope. So we also test that. So with the telescope, of course, we're looking for signals from the cosmos, but actually we have a lot of background. And this background is different things. For example, first of all, bioluminescence. So in the sea, there is little algae and organisms that create light, and we detect that. So we have to remove that from our data to be able to see what we are interested in. That's one thing. Another thing, for example, is the salt from the water. This also, when the salt decays, it produces light, and we also detect that. We also have to get rid of it. And another source of background, and the biggest one, is some particles that are created in the atmosphere. and those are called muons. So when other particles that we call cosmic rays come from the cosmos and go through the atmosphere and interact, they create a bunch of particles. And one of those are muons, and we get a lot of muons in the detector. So there's a lot of work in understanding our data, removing those muons to try to see the cosmic neutrinos that we are interested in.
Well, now we know how the detector is working. The big question is, what have they actually discovered? And this is where it gets really exciting. But before we go into that, I want to give you a quick refresher on metric prefixes. And it's important, I promise. Now, you might be more familiar with these terms when used in relationship to storage. So if you have a gigabyte, a few of these are going to give you a 4K video. If you have a terabyte, this is probably what you're using to describe the storage drive in your computer. And then we have the petabyte, which is 1,000 terabytes or 1 billion gigabytes. And that's a lot of data. And we use the same prefixes for energy in particle physics. So we have the Higgs boson, which has an energy of 125 giga-electronvolts. And this is just a unit that physicists love to use in particle physics. And then the Large Hadron Collider is accelerating protons up to an energy of 6.8 tera-electronvolts. And if you had something at peta-electronvolts, well, that's around 1,000 times more energy than the Large Hadron Collider is accelerating protons to. Okay, back to the result.
Yeah, let me first say what you see here is 21 of these lines. In the end, we want to build 10 times as much as that. So this is really only the first stage of the detector. We are building it still, but already indeed we have discovered something extremely exciting, and it's in fact this particular event. And basically what's exciting about this is just the amount of light that the neutrino has produced in the detector. So all these blobs. From this amount of light we can reconstruct what the energy was of this muon particle that was there. And the answer is it's in the region of 100 PeV, peta-electronvolt, which makes this the highest energy neutrino ever detected in the history of mankind. And in fact, since this is an elementary particle, it's actually the highest energy elementary particle ever detected. So this makes it very exciting, and also we did not expect to see this yet, because as I said, we only have a small part of the detector. There's another experiment on the South Pole doing similar things. They have already been measuring for 10 years and they never saw anything like this. So it's an exciting discovery. It's also at the same time a little bit of a puzzle, like why do we see this? Well, others have not seen it yet. But yeah, this makes it exciting, and the question is now, where did it come from and how was it produced exactly in the universe? So that's a question we still have to start answering at this point.
Yeah, the event is extremely special for us because it will turn out to be the highest energy neutrino event ever observed in the world, ever. So that's exciting because it opens up a new energy regime that nobody has ever probed. And it looks like we're probing an energy regime where the origin of these neutrinos could be very different from what we have seen before. Something that we call cosmogenic neutrinos, and they come from interactions of the ultra highest energy cosmic rays with background photons in the universe. Now, we're not sure if one event will be that, but we open up a new regime and it could be extremely exciting.
Yeah, I think it's a boost of energy and excitement. Like we could see it in the collaboration that when this was announced, there was a lot of work from many different groups, like from the calibration, the simulations, the data analysis, in all the stages. People felt very excited and tried to understand even better how our simulations, calibrations, and understanding of the detector playing a role in understanding this event. So I think, motivated and hopeful to see what's coming.
So to summarize, the KM3-NET collaboration have announced the observation of the highest energy neutrino ever recorded. It created a muon near the detector that came in horizontally and lit up the detector like a Christmas tree. And it's possible that this high energy neutrino came from a different cosmic accelerator source than the other neutrinos already discovered. And it could even be a cosmogenic neutrino. Now, results like these are only possible in huge international collaborations with scientists and technicians and engineers from all over the world coming together to construct these complicated detectors in such difficult environments. So I wanted to ask my colleagues, what do they love about being in a collaboration like this, apart from the really interesting results?
What do I like from Chem3Net? I like that it's a big collaboration, but not as big as the ones we have, for example, at CERN, at the big particle collider. So I know almost everyone in the collaboration, so that's nice. And every collaboration meeting, we meet each other and I can talk with a lot of people. I like that it's an international collaboration also. So we have people over Europe and also beyond. And I particularly like the experiment because we're not creating the particles that we observe ourselves, but we're just a telescope. So we wait for particles coming from the universe to understand them and also do some astronomy.
So the technology is, of course, it's crazy. When I heard that it's possible to build such a thing on the bottom of the sea at 3 kilometers depth, that was really fascinating. And the other thing I like is that it's really a nice mix of particle physics and astronomy. So we can really, by building these detectors, you can really do both things at the same time. We study fascinating astronomical objects, so these cosmic accelerators are most probably driven by matter accreting on black holes, and then somehow this matter is ejected there. So those are fascinating things to think about. And at the same time, I'm really interested in the particle physics properties of these neutrinos themselves, because they are actually the only particles that sort of deviate from the standard model of particle physics. So in the next years, neutrino research in general will be a very exciting field to be working in.
And so, as you've just heard, this discovery is only the beginning. The KM3Net detector is still being built. And as it continues to grow, it will allow scientists to discover even more of these highly energetic neutrinos, unlocking insights into the most extreme particle accelerators in the cosmos. And whether it is detecting neutrinos, searching for dark matter, or learning more about black holes and supernova and other incredibly highly energetic events, experiments like KM3Net are changing the way that we understand our universe. And as someone in particle physics, but who basically has to just ignore all of the neutrinos that come from our experiment, I find it incredibly inspiring to watch my colleagues build this detector and learn more about these incredibly fascinating, tiny, elusive particles. If you have enjoyed this video and want to hear more about groundbreaking new results in particle physics and about the detectors and the machines that means we are able to do these studies in the first place, then make sure to like, subscribe, and all of the things that you need to do in order to tell the algorithms that be you want to see more of these videos. And if you have any questions, then of course, put them down in the comments and I will be happy to answer them and talk particle physics with you to our heart's content. Thank you so much for watching, and see you in the next one.